Thanks to the organizers for giving me the opportunity to visit this beautiful city, which I've been here for 20 years. So I want to talk about the Hitchin fibration. So I was asked by the organizers to keep it extremely elementary, so I apologize in advance. There will be no new results. This is just an introduction to this object. I'm talking about this object since, well, it's a completely integrable system in an algebraic sense. And this integrable system has many ramifications in algebraic geometry and in differential geometry, since it is an example of a hyperkähler variety. And also it has important ramifications in representation theory. And for representation theory, there are at least two directions in which this object is important. One direction is that this system plays a crucial role in Gauss' proof of the fundamental lemma, which is something I don't really understand. And it has also an important role in the theorem due to Beilinson and Drinfeld on the quantization, which is a subject of which I have no understanding whatsoever. So I won't talk about these things, and I'll just tell you how the Hitchin fibration arises. And well, let me just say a small thing about this. So the link between the Hitchin, well, first of all, the Hitchin fibration is not a fibration in the usual sense. Fibration usually means that all the fibers are isomorphic. This is far from being true. There are singular fibers. And the singular fibers of the Hitchin fibrations are very strictly related to an important subject, to an important object in representation theory, which is the affine Springer fiber, which was introduced by Kashdan and Lustig, and the relation between the fibers of the Hitchin system and these affine Springer fibers was probably first noticed by Gérard Lomon, and that's precisely this direction, which makes it is precisely this direction which makes the Hitchin fibration important. So I'll try, as I said, to be very elementary. So let me start with the first thing, which is called Abelianization. So we start with C, so say a compact Riemann surface of genus G. So this is by an easy version of Serre-Gaga principle. This is the same as a non-singular complex algebraic curve of genus G. And so the object we want to, so an example is just you take a planar curve in the projective plane with f such that the zero locus is non-singular. So, well, let me remind the definition. Either analytic or algebraic vector bundle, say V on C, is well, is a map from V to see, either analytic or algebraically, which is locally in the analytic or Zariski topology, something like an open set times R-dimensional, so V of rank R so locally it's a product of an analytic neighborhood or a Zariski neighborhood by CR, and by, again, by the Gaga principle, these are the same. Okay, locally trivial in the analytic topology and locally trivial in the Zariski topology are equivalent. So I will talk of a vector bundle without specifying either analytic or algebraic category. So if R equals 1, this is called a line bundle. So it's classical terminology. A mano, è tanto che non insegno in quest'aula. Forse non ho mai insegnato. So, from the topological point of view, there is a unique invariant which is the so-called degree, which is an integer. And this may be understood as follows. If you take out a point from your Riemann surface, you have something which retracts on a one-dimensional CW complex. Okay, you take out a point and then you retract into a wedge of circles. So the vector bundle is topologically trivial over this open set. Then you have a disk over this puncture, and the vector bundle is topologically trivial as well. So the only thing you have to do is to fix the clutching function, the gluing function, on a punctured disk. And this is given up to homotopy by how many times circling around the punctured disk circles in GLN, in GLR. Okay, so this is a number. It's basically, the only homotopy invariant thing. And, okay, and this is also, by the way, this is the same as the degree of the top exterior power. Well, for a line bundle, another description of the degree is the following. You take a general differential, say, section or meromorphic section. Well, say, I'm interested in the holomorphic category. So you take a general meromorphic sections, and you count zeros and poles, and you add up, and that's the degree. Okay, so how many vector bundles are there on such a Riemann surface? So if G equals 0, then the answer is simple. So if Ln is the unique line bundle on the projective line of degree n, it is a theorem, actually, an easy theorem that on P1 of C, the degree identifies the line bundle even holomorphically. So then a theorem which is usually attributed to Grothendieck, although it goes much earlier, is that any vector bundle splits as a direct sum of these line bundles. Okay, this is actually quite simple, and for G, if G equals 1, then Attia, back in the 50s, I think it was 57 or so give a classification of vector bundles on an elliptic curve. For the genus from 2 on, then this is much more complicated. So one usually, I mean, either you look at vector bundles over a given curve as a stack, which is something I don't want to do today, and probably I don't want to do ever in my life, and or you take a more elementary approach, and then you impose, you restrict to what are called semi-stable. I will define this notion later. Bundles. And then there is a moduli space something like NRD, so R is the rank and D is the degree, which is an algebraic variety, actually a projective algebraic variety of dimension R square G minus 1 plus 1. Okay, the dimension can be computed by Riemann rock. So there is an algebraic variety which parameterizes not all vector bundles, but semi-stable vector bundles, and also the notion of parameterization is somewhat subtle, and I don't want to discuss it now. And let me end this. Pardon me? Yes, because the tangent space is H1 of endomorphisms of E, so that in the endomorphism, degree cancel. I mean, E times E dual, so the degree cancel. What is not independent of the degree is whether this space is singular or not. Because if D and R are co-prime, then it's non-singular. Otherwise, it's singular except the case of rank 2 and degree 0, which is non-singular by mistake. I mean, it should be singular, but it's not. Okay, so the remark is that a vector bundle on C is the same, rank R is the same as a locally free sheaf of OC modules of rank R. Okay, so why Abelianization? So vector bundles are the same as torsor over GLR, which is non-abelian, as you might have noticed, if R is bigger than 1. So the case of rank 1, the case of line bundle must have something special, and this is in fact very classical. I will spend a few minutes recalling you how things go. So in this case, well, first of all, remark that vector bundles of rank 1 up to isomorphism form a group. You may tensor 2 line bundles and you still get a line bundles. So line bundles over a Riemann surface, let me call it X now, because later I will use line bundles on a curve which is not C. So let me introduce a different name. Say of degree 0 are parameterized in a kind of a subtle sense. I mean, if you want to say what is the universal property, you have to suffer a bit by this object P0 of X, which is a G-dimensional complex torus, actually more than a complex torus, an abelian variety. And for degree different from 0, well, pick D of X is, I mean, it's not, so this is a group because you have an origin. You have the trivial line bundle, which is an origin. So for different from 0, there's no such an origin, so this is what is called a torsor. So it's something like an affine space is to a vector space. So it's a group without picking up an origin. And it is important that pick 0, it's basically the main theorem of Hodge theory in dimension 1. So pick 0 as a complex torus has an explicit description as the quotient of an affine space by a lattice. So this is the lattice generated by periods of holomorphic one forms. Okay, so genus G means that you have a basis omega 1, omega G of holomorphic forms. So on the other hand, you pick a basis of the first homology group with integral coefficients, and then you integrate. Okay? And then you have 2G vectors which span a lattice, and when you mod out, you have the description of pick 0 in this sense. Okay? So this is classical. And I mean, this is a mixture of theorems of Abel, Jacobi, and all such people. Let me also remind you that, since I will need it soon, that if X is a singular curve, you still have an algebraic group parameterizing degree 0 line bundles, but this is no longer compact. Okay, so as such, by a theorem of Chevalier, so this is a connected commutative algebraic group over the complex number, so it's an extension. So it's an extension of an abelian variety by something which is a product of some additive groups and some multiplicative groups. Okay, so over C, these are the only connected affine commutative algebraic groups. Okay, and so still in this case, even though it's not compact, there is a way of compactifying it. And this is called the compactified Jacobian. So here I'm saying this, but there is a considerable amount of dust that I'm sweeping under the rug, because, I mean, this is false, okay? So there is a natural way of compactifying this if X is planar, so locally it's a curve traced on the surface, so that equivalently the Zariski tangent space has dimension 2, and this compactification is unique if X is irreducible. Otherwise, one has to choose a notion of stability, and things get a bit complicated and technical. But so this is just true only morally true. Okay, so let's say that this picture, in a way, of course, this is no longer a group. Okay, so basically we are compactifying, so we are acting some objects at the boundary of line bundles. So basically, the peak zero is not compact because you can have a sequence of line bundles which degenerate to something on a singular curve to something which is no longer a line bundle. And you take these objects as the boundary points, and these objects are basically torsion-free rank 1 sheaves. Okay? If a curve is non-singular, torsion-free is the same as locally free, because on a DVR, every torsion-free module, etc., etc. If the curve is singular, there are torsion-free modules which are not locally free. So you are adding these torsion-free sheaves at the boundary. And this is no longer a group, because when you tensor two torsion-free sheaves, you don't get a torsion-free sheaf. Okay? And there's no way to fix it. So let's say that rank 1 is well understood. So the point of Abelianization, is basically to construct rank R vector bundles on C from rank 1, so from line bundles over a different curve. So let me be a bit more specific. So assume the C prime to C, let's call pi the projection. This is a degree R, maybe ramified, covering of C. So C prime is another Riemann surface, but maybe it's good to consider also the case in which this is singular. So let's say at least that it is reduced. So maybe singular, but reduced. So saying that this is a degree R ramified covering means that you have down stereo curve C, and at some points you have R points, which maybe at some point collapse badly. I mean, they can do all sorts of things. Okay? But at least generically you have R points. Now, the idea is very simple. So, say that L is a line bundle on C prime, and define what is called the direct image of L over C. So over the point C, you take the direct sum of the fibers X at the inverse images of C. Okay? Well, here you need some care at the ramification points. A priori. But actually you don't. You don't need some care because there is the language of algebraic geometry which tells you the following. So this map results into a map of sheaves of this kind, and so here I should have said flat. So this map makes OC prime into a locally free rank R sheaf on C. So a line bundle on C prime is the same as a rank 1 OC prime module. Okay, and then you are just restricting the scalars. Okay, so you are just considering that you multiply only by functions in OC, and therefore it becomes a rank R, locally free thing. Okay, so restrict scalars and get a rank R locally free sheaf on C. Okay, so from a rank 1 module over this sheaf of rings, you get a rank R module over this sheaf of rings. And this is the concrete, I mean, a more concrete way of thinking. Okay? And of course you may think, okay, so this is a stupid thing, I'm taking the direct sum. No, you're not. Because you're taking the direct sum over a point, but then when you go around, these points get interchanged, so it's not a direct sum. It's not globally a direct sum. Okay. Now, so this is a way to construct vector bundles, and I mean, easy as it is, this was, I mean, it was first noticed by Beauville-Narasimhan and Ramanan, that this construction is actually very effective. And basically, you can choose, they prove that you can choose a curve so that basically every vector bundle, almost every vector bundle can be obtained this way. Now, oh, maybe I should remark here that, I mean, from this algebraic construction, okay, so this construction works also if C prime is singular and the sheaf on C prime is torsion free. Why? Because if I have a torsion free sheaf here, so this is maybe not locally free, but when you restrict the scalar, C is non-singular, so it's torsion free over a non-singular, and so it's locally free. So you don't care about if it's not locally free here. That's quite useful. Okay. So to construct vector bundles, we have to look for ramified coverings. Okay, so now here's what we do. So we can start, I mean, how do you construct coverings? One way to construct coverings could be the following. You take, for instance, a surface which projects to your curve, C, and then you take some curve traced on the surface, and then you restrict the projection. So one way to take a surface projecting to C is to take a bundle over C. And just in order to make the minimum number of choices, let's take something canonical. So let's take the cotangent bundle. So let's take S, the cotangent bundle of C. So we have C sitting here as the zero section. Of course, here there is a guiding principle for this choice, and the guiding principle is maybe goes back to Mukai, which observed that moduli spaces of sheaves. So this is a symplectic surface. It's a cotangent bundle, so it's a very symplectic thing. Okay, and the Mukai principle says that if you look at objects, at moduli spaces of objects over some symplectic surface, you get symplectic varieties. Okay, so this is a philosophy which can be made precise. Now, so to construct a few coverings, you can do the following. So pick A1, a holomorphic one form here, A2, a quadratic differential, and so on up to EAR R times differential here. So these are all line bundles. Omega 1 has rank 1, so tensor pairs still have a rank 1. So by Riemann rock, there are plenty of these. Well, and if you count by Riemann rock, how many they are actually a vector space of dimension n squared g minus 1 plus 1, which if I hadn't erased, is precisely the dimension of the moduli space of vector bundles. Now, so pick a local trivialization of T star C. So say that X is the coordinate on C and Y is the coordinate, the fiber coordinate. Okay, so maybe they should call it Q and P, but X and Y. And so these things here locally are written as some holomorphic functions times the local basis. Now write the equation y to the n plus a to the r, sorry, did I write r? Yes. Plus a1 of x y to the r minus 1 plus blah 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 plus ar of x equals 0.
Sorry, what is
N is R. Throughout this talk, N equals R. Is the rank. Probably, I hope I have been, era giusto. Almost consistent everywhere. Okay, so consider this inside the cotangent space.
What is this equation?
A polynomial. So you have coordinates x and y over an open set, and you consider the zero locus of this polynomial. Okay? So the point is that since these AIs live here, these equations glue. So these local equations glue very well. So this define a set. So this is given in local coordinates, but actually the zero set is well defined. Okay? And this is called, well, let me denote by CA. So say that A is this collection. A, underlined A, is this collection A1, AR. Okay? So this defines this CA, which is called the spectral curve, a spectral curve. And
Why there should be such a polynomial relation?
Such a polynomial?
Why should be such a relation?
No, I'm just considering the locus defined, the zero locus of this polynomial.
Just arbitrary.
Yes, I pick this element, a holomorphic one form, a holomorphic tensor, and then I consider the zero set of this polynomial. So the point is that since I'm considering this inside the cotangent bundle, when you look at the transition functions, so these AIs, so AI of x will be something like AI x prime times dx over dx, no, dx prime over dx to the I. There will be some transition functions like that. But these are precisely the transition functions of y. So that these equations glue. So they define they give a well-defined locus. Okay? So now, clearly, CA, which sits inside the cotangent bundle, maps to C. And at least for generic AIs, this is actually, well, actually we are going to consider all possible AIs, but this is actually a non-singular Riemann surface of genus, and this is an R21 cover. This is generically an R21 cover because if you take a generic X, there are R roots. Okay? And then, surprise, surprise, when you compute the genus, you have a junction formula for curves traced on a surface, you compute the genus is, again, the magical number here. So things begin to be very symplectic, very completely algebraic. You have a parameter space for spectral curve, which has this dimension. Over every point, you have a curve which has this genus. And if you consider its peak 0, this is going to be a complex torus of this dimension. So this begins to look like a torus fibration, like, I mean, a completely integrable system. Okay, and that's actually precisely what can be done. So, but still, at this point, the construction I said before, this so-called BNR, so Beauville-Narasimhan-Ramanan construction gives a map from peak 0 of CA, so from line bundles on CA to rank R vector bundles on C. Okay, plus something. So in this plus something is a cool exercise of the linear algebra we are so proud to teach to first-year students. And it goes as follows. So let's look at that map there. So we have this map here. This equation says that OC prime is the same as OC, then you adjoin the variable, and then you mod out by an integral relation. So if you start from a, say, locally free rank 1 module here, and you look at it as a locally free rank R module here, there is a piece of structure which you're missing, which is the action of Y. So from a rank 1 module here, you get a rank R module here plus an endomorphism. Now, linear algebra question, what is the characteristic polynomial of this endomorphism? It's precisely this. There are a few things to be fixed, but this is basically true. Okay? And vice versa, if you have a rank R module here plus an endomorphism with characteristic polynomial, that one, then you can make it into a rank 1 module over this ring. Okay? So this is also, this plus something is that actually this gives rank R vector bundles. I didn't say anything about the degree. The degree can be computed by Riemann rock, but it's not very relevant now. Okay? Plus an endomorphism theta, so let's call the vector bundle E, plus an endomorphism theta, and if you compute precisely the transition functions, you see that this is not really an endomorphism, it's a twisted endomorphism, so this actually lives in H0C endomorphism of E tensor omega 1 of C. So it's an endomorphism with coefficients in 1 forms. So this is called the Higgs field. And of course, why this is called the Higgs field is completely unknown to me, but doesn't really matter. Okay, plus theta, and theta satisfying this equation. Okay, so this is the procedure of Abelianization. From rank 1 objects on a spectral curve, you get Higgs bundle, so the pair E theta is called the Higgs bundle, where theta satisfies precisely the spectral curve. So you understand why it's called the spectral curve, because basically over every point of C, the R points upstairs are basically the eigenvalues of theta, right? So as soon, I mean, generically these are distinct, so they're precisely the R eigenvalues. So the spectral curve is given, I mean, going back, if you have theta, you get the spectral curve by looking over, I mean, at least on the generic points, looking at the R eigenvalues and then closing up to a Riemann surface. Okay, so now it's time to clean up things, and I start by cleaning up the blackboard. So the final product is the following. Let's see. Oh, maybe I should notice a spectral curve can very well be singular, can even very well be non-reduced. For instance, if you take A1 to AR to be 0, then you have Y to the R equals 0. So you have a sort of a fattened zero section, okay? And over non-reduced spectral curve, what happens over non-reduced spectral curve is a complete mess, which I have I've thought a lot about it, but I haven't reached any reasonable insight. So we can clean everything up. So we start from A, and this is we collect all, so we collect all possible spectral data. Okay, so this is the same as C to the R squared G minus 1 plus 1. So over A, you consider sort of the universal spectral curve. Let's call it P. So by this I mean that P minus 1 of a point A is precisely the spectral curve CA. Okay, you consider all possible spectral curves. Okay, keep it here for a moment. Well, now you can do something like that. So at least on the open set, let's call it A red. So these are the spectral data such that CA is reduced. So at least over this open set, you have the group scheme pick 0 C, what did I call it? A over A. So by this I mean that over the point A, I consider pick 0 of CA. Okay? So this is a group scheme over A, while over A red. and dangerous curve. This is not a proper map. This is not a proper map because when the curve is singular, its peak zero is non-compact. It may be non-compact. Okay? So as my longtime friend Angelo Vistoli says, working with a non-proper map is like being on a roller coaster where some bolts are missing. Okay? So we want to put all the bolts back. But this is a group scheme. And this can be made into a proper map by considering the relative compactified Jacobians. So now we have, let's say, peak 0 C A over A compactified over A red. And by what I said so far, to every point in this here is associated a Higgs bundle. Right? So every point here is a torsion-free sheaf over some spectral curve. So I push it forward and I get a Higgs bundle whose characteristic polynomial is given by the point I'm projecting to. So we have this. This is a proper map over which this group scheme acts relatively. But actually more is true, and this is, I think I'm going through towards the end. How much I have? 8 minutes or something?
Yes.
Okay.
Okay, maybe 6 minutes plus 5 minutes for questions.
So I have less than 8 minutes.
Okay.
No. Okay, but I'm almost done. Actually, the final result is, which is due to many people. I mean, obviously, the most important contribution is by Nigel Hitchin himself. So there exists, so theorem, there exists, let me remark also this. Over the open set, where the spectral curve is non-singular, here there's no need to compactify. We already have something compact, and we have an abelian variety, a complex torus. So this is a torus fibration over a big affine set, okay? So the theorem is the following. For every R and D, there is a moduli space called MRD of rank R, degree D Higgs bundles, semi-stable. Unless you ask me, I won't tell you what a semi-stable Higgs bundle is. It's just that you cannot consider all Higgs bundles of a given rank and degree if you want to have something of finite type, separated, and so on. You have to restrict to semi-stable things, Higgs bundles. So which is one, a quasi-projective variety of dimension 2 r squared g minus 1 plus 1. It's an even number. Okay? And plus h from MRD to this affine space A, which is a proper map. Actually, it's a projective map. It's more than a proper map. This is called the Hitchin fibration. Plus MRD contains as an open set, Zariski open set, the cotangent bundle of the moduli space of vector bundles. Remember, this was the first object I told. These are naked vector bundles, no Higgs structure. So this is some sort of a partial compactification of the cotangent bundle. And as every cotangent bundle, it has a symplectic structure. And this symplectic structure actually extends to here. So this has a symplectic structure. Holomorphic symplectic structure. And this has dimension r squared g minus 1 plus 1. So it's half the dimension of here. And actually H is a Lagrangian fibration. I'm neglecting a few irritating facts about singularities, which I'm willing to discuss if you really want, but okay. And actually, there is an action of the group scheme the relative over A. So an action fiber by fiber, and this action is Hamiltonian. So this action is Hamiltonian, and H is actually this is really the Arnold-Liouville map. Okay, so this is a Lagrangian fibration. You have a group scheme. The action of the group scheme gives the fundamental vector fields along the fibers. And so this is the action which associate to your variety, or what are they called? Action variables, action angles, action variables. Okay, so this is really an algebraic completely integrable system, and in my opinion, is the most beautiful algebraic completely integrable system one can imagine. And before closing, just let me say that what I told you is the picture for the group GLR, but there is a similar picture, although I mean, more subtle but very similar picture for every reductive group. And I think that's all.
Okay, let's send the speaker. Any questions?
Can you give a hint how bad or how good are the singularities?
Are you interested in the singularity of the modular spaces or of the fibers? Because both questions are extremely interesting. Okay, the modular space, if R and D are coprime, no singularities. Otherwise, I think what is known is that they are Cohen-Macaulay. I'm not sure if it's known that they are rational. That's it. For rank 2, so there are a few cases in which I think rank 2 and genus 2, you have actually a symplectic resolution. So it's a semi-small resolutions. In that case, you can really write down the equations that they are complete intersections. They are manageable. Otherwise, yeah. I think that not much is really known. I mean, maybe by general principle, maybe you have Cohen-Macaulay things, but nothing. The singularities of the fibers of the Hitchin fibration are extremely interesting because they are the singularity of affine Springer fibers for the group. So the theta, the Higgs field is basically the element which you use to define the affine Springer fiber. Affine Springer fiber associated with what is it? I don't remember, topologically nilpotent something on the affine Grassmannian.
Also questions? So what is the boundary of that set here?
Here. It's a mess. I don't know. Because, I mean, so basically, so n, so here is 0 inside A. So 0 inside A contains n, and then contains some mysterious stuff. So this is what is called also the nilpotent cone. It's something very important. So there are n and then many other components. And then from every n, so n sits inside M by considering the Higgs bundle, the Higgs field to be 0. Then you let the Higgs field go, because, I mean, if it's stable already, it will be stable. And then these fibers do something completely weird. And then you have to consider all these weird fibers, and what is left. I mean, you can say what they are. So they are Higgs bundles, which are semi-stable, has Higgs bundles, but not as vector bundles themselves. So the definition of semi-stability of a vector bundle means that there is no subbundle which transgress an inequality. The definition of a semi-stable Higgs bundle is that there is no such bundle which transgress this inequality and which is invariant by the Higgs field. So, from the modular point of view, you know what they are. These are bundles which are stable as Higgs, but not as naked vector bundles. But, so what? I mean, it's very hard to study them.
You said that you can generalize to other groups, and you did it for GL.
Yes.
Right. How do we see the GLR acting here?
I mean, a vector bundle is a GLR torso. Yes.
That's because of that.
Yeah.
But then if you restrict it,
Then if you restrict, for instance, I mean, already considering SL and PGL is a mess, because then instead of the whole Jacobian, you have to consider only the prime variety. But when you do SL, you consider the prime as a sub-object. In the PGL, you consider the prime as a quotient object. And already at the singular fibers, you have different behaviors, and then there is this principle that for Langland's dual group, the Hitchin fibrations are dual. I mean, dual abelian varieties on the smooth locus and dual compactified prims. And then there's all, I mean, every group has its flavor. For instance, the description of G2, I don't remember it, but the only thing I remember is that it's fantastically beautiful, okay? And I mean, so in general, instead of considering the whole peak zero, you have involutions on the spectral curves, and then you consider only line bundles which are stable by these involutions.
But for us exceptions, you cannot look for EA.
Yes, you can. You can. I mean, so you have to talk about a space classifying Higgs torsors for E8, and then you have something which is not the spectral curve, is something which is called the cameral curve, which is basically, you know, in GL it would be like going from the spectral curve to its Galois completion. So you have an action of the Weil group of your group, and then you play. Yes, and then you consider rank 1 objects on this cameral curve, and then you ask for Weil invariance and so on. And it's really, it's complicated. I mean, for classical groups, there is a concrete description which goes back to the article of Hitchin on Duke. Otherwise, there's the description, I think that, I mean, the description, Ngo gives, in his big paper, gives a good description of how this cameral curve works.
Okay, maybe let's send the speaker again.